Hello, everybody, and welcome to another Communication Systems Laboratory seminar. We're excited today to have Phillip Mohr here to talk with us about low complexity LDPC decoding with mutual information maximization. We're really excited about this topic because it's so closely related to the work that we do in the group on efficient LDPC decoders, and also because this is a continuation of a great relationship that we've had with Hamburg University of Technology and Gerhard Bausch's group starting with Max Stark working with Linfeng Wang on information bottleneck inspired approaches to LDPC decoding. So anyway, without further ado, here is Phillip.
Yeah, thank you, Rick, for the nice introduction. Today's topic will be centered around low complexity LDPC decoding with mutual information maximization. Okay, now the pointer works. And related to that topic, I will present the most recent works of our institute. And the talk is therefore structured as follows. So first, I give an introduction to the LDPC decoding, and then we have three parts, and each part is related to a publication we did in the last year, and there's some dependency between them. And first, I will start with the uniform versus non-uniform quantization topic, followed by a check node aware variable node design for 2-bit LDPC decoding. And we finish with horizontal and vertical layer decoding and their opportunities. And finally, I give a glimpse on future work. And I will now start with a short introduction. I think you are all very aware of that topic, but it's important to have some common ground. And LDPC codes are used in many applications, and a typical model is depicted here at the top, where we have some information bits and that shall be protected by an encoder. We add some parity bits here that fulfill the parity check constraints. And then we have a channel, and we get an output messages here, which might contain errors. And the decoder aims to remove those errors by exploiting the constraints. And a very useful representation of the parity check matrix is known as a Tanner graph, where we have a set of check nodes and a set of variable nodes. And the variable nodes represent the code bits here, and the check nodes represent the parity checks. And the connections are defined by the parity check matrix. And typically, a message passing is performed to do the decoding here. And in that process, we exchange messages between the variable and check nodes, and in between updates are performed. And actually, this process causes major parts of the receiver's resources. Actually, it's the most complex part of the whole transmission here. And the area and energy efficiency of that process is mostly determined by the amount of exchanged bits and the complexity within the node operations. So we are highly interested in reducing both points here. The first point refers to the bit width of the messages, and the second point refers to the node operations. And in this first work, we will focus mostly on reducing the complexity of the node operations. And this work has been recently presented at GlobeCom. And at first, we will look at the variable node update within this Tanner graph here. So a quantized mutual information maximization update can be performed the following way. So, for example, we receive here an extrinsic message from a check node and a quantized message from the channel. And we want to compute an output message, which shall have low resolution too. And several works here proposed to use an update in a so-called computational domain, where we translate the quantized messages to higher resolution representation values, and we can add them up so we have a single high resolution number. And at this point, we have no loss in mutual information. And we can now perform a quantization operation to reduce the bit width. And now the goal is to keep the mutual information as high as possible with respect to the message here, the compressed message, but still having low resolution. And this is known, or was discovered to be, an information bottleneck problem. And we use an information bottleneck algorithm from Mohr to solve the optimal quantization here. And the goal is to maximize the mutual information between the relevant variable x and the compressed variable t here. And one example for such an optimization is depicted here, where we have a joint input distribution, which describes the relationship between the observed variable and the relevant variable x. And here I just use a Gaussian distribution. And we can see that the quantization is determined just by those vertical boundaries here. And the maximization of the mutual information tweaks those boundaries to get the maximum of mutual information. And actually, one can show that it is sufficient to use those threshold levels if the input is sorted according to the log likelihood ratio. And so the optimization just moves those boundaries until the best solution is found. And now we are looking at an implementation of such a mutual information maximization update. And instead of using real valued numbers, one would rather use scaled integers with a limited internal bit width to keep the hardware complexity not too high. And what we do is we just scale the real valued integers with a parameter here. And we can then perform the translation as presented earlier. And then we have an integer addition, and we get an integer number. And now this number shall be quantized. And since we restrict here to symmetric quantization, we can just copy over the sign bit in a sign magnitude format. And we just need to quantize the magnitude part. But if we do that, we need to compare against those non-uniform threshold levels.
And so quickly, so just to make sure I'm clear, what's happening from the blue arrows going into the box and the red arrow coming out of the box, you're converting the non-uniform quantization into a uniform quantization of higher resolution. Or is that right? Or am I missing something?
Yeah, in principle, what we are doing is we convert first to log likelihood ratio representation, and then we just perform the addition to get number which has, of course, higher resolution, because if you add multiple numbers, the bit width increases. I'm not sure what you mean by the uniform.
I think I'm calling phi sub delta is like a uniform quantization of the non-uniform. So you take the t value, which is a non-uniform quantization. You convert it to the likelihood, the best reproduction vector likelihood, which you then uniformly quantize to get the phi. And actually I was wrong. So the thing that's happening in the box is actually adding up all the phi's from all the different variable nodes coming in, or all the different edges coming in. And then you finally just compute the sign.
Yes, so the non-uniform part here does refer only to the quantization, not to the computation we do here. But
Right.
you are right, you can see this as kind of some uniform quantization when we do the rounding operation here. But this is this can be neglected for now, I think. So we just do here the computation, and then we have some non-uniform quantization here. And this non-uniform quantization is what this talk is mainly about. So here we need to quantize this high resolution number, which has, for example, the 9 bits here, to a 3-bit number. And to do that, we need to compare against those threshold levels, which have been found by this optimization. And to realize this in hardware, we need comparison operations. So we compare against this middle threshold level and see if we are on the left or right. And then we need a second comparison to see if we are left or right of this tau 1 or the tau 3. And this is just the introduction to explain where complexity arises in the non-uniform quantization approach. And on the next slide, I will show a solution which can get rid of this complexity here without much performance degradation. And so if we look at this pattern here of those boundaries, we saw that this is close to being uniform. And then we just said, okay, let's restrict to uniform mapping and see how the result will look like. And it's very similar. And now the question is, can we gain something in practice out of it if we do this restriction? And the answer is yes, we can gain a lot if we look at the quantization of this high resolution message. So in order to do the uniform quantization, we just need a few logic gates and to get to the compressed message, because it's now just a right shift operation and a clipping operation. And we can move those boundaries by tweaking the scaling factor here at the translation. So this is the trick we do here. And so we end up with negligible quantization complexity. And we also include the internal bit width here in the optimization. And what we pay is a slightly reduced mutual information preservation. And this is the overall idea of this first paper.
That's a good idea. I like that.
Yeah, thank you. So if we look at a real world example where we have a high rate code, we can do the optimization with the non-uniform boundaries and compute the output mutual information. And we can also do it with the restriction to the uniform boundaries. And we see that the mutual information just is different after the 4th decimal place. So from those figures, we can guess that the uniform quantization will work very well and close to the non-uniform solution. If you look at those pictures here, maybe one might have the question why those boundaries are close to the decision threshold. So this is one further question I digged into, and the answer is that the quantization errors in unreliable regions lead to higher mutual information loss. And therefore, those boundaries are more dense, close to the decision threshold. So actually what we depicted here is just the positive part here of the input. The negative part is mirrored, but it's not shown here. And
Philip?
yeah.
I have a question. So the observation you made that the non-uniformity is not giving you much gain in terms of the mutual information, is this dependent on the channel SNR, or are you saying this is true across a variety of SNRs?
So in this work, we restricted to regular LDPC codes, and I've done simulation with a medium rate code and a high rate code. So for those SNR levels, it seems to work very well, but I have no mathematical proof that it will work well for every input distribution.
Thank you.
Thanks for the question. Yeah, and actually the placement here of the boundaries can be explained by looking at the optimization criteria. So what we want is to minimize the loss of the mutual information at the input and at the output. And yeah, we can reformulate this equation and see that we have here the addition over the Kalbach-Leibler divergences, which measures the similarity between the quantized representation and the observed representation. And we can see that if we have a large quantization error for reliable messages, the contribution of this Kalbach-Leibler divergence is still close to 0. So we can have low resolutions for the high reliable messages, but we need a higher resolution for the low reliable messages. So just to give you some intuition why those boundaries look the way they are here.
Can you, sorry, let's check. I wanted to ask, when you are saying the Kalbach-Leibler divergence between Ly and LT, so those are likelihood values, those are numbers, and the Kalbach-Leibler distance is between distributions. And so I know that you are using Ly and LT to induce the distributions that you're going to compute the Kalbach-Leibler divergence for, but could you just clarify for me? I have a guess, but I'm not gonna voice it. I'm just gonna ask you to tell me, how do you get the distributions from Ly and LT that you then compute that Kalbach-Leibler divergence with?
We can obtain the distributions by the definition of the log likelihood ratio. So we have the log likelihood ratio as defined as the logarithm of P0 divided by x equals 1. And from that, we can resolve to the probabilities again.
So just to clarify, the Kalbach-Leibler divergence that you're computing is between two different PMFs for a binary random variable.
Yes, yes.
Good, thank you.
So the results we have seen so far are just for the variable node. And yeah, there exists a computational domain also for the check node. And we can apply the same technique also at the check node to reduce the complexity. And at the check node, what we typically have is that in this case, it's the degree 3 check node. We have those 3 variables, and we can obtain extrinsic information about x from B2, XOR B3. And this can be used to derive such a computational domain update using the extrinsic messages. And again, we obtain a high resolution number like for the variable node. And the quantization can be seen again as an information bottleneck problem where we have an observed variable, a compressed variable, and a relevant variable, which is the x here. And yeah, this can be solved by an information bottleneck algorithm. What we will do in the next slide. But in practice, often you don't use this update because there exists a more simple update, which is known as the minimum approximation, which avoids high resolution numbers completely. And I gave it here as a hint because it's very important for practical implementations. But now let's stay at the computational domain implementation for now. And yeah, here again, we can make similar pictures as before and see that the mutual information barely changes if we make a restriction to the uniform spacing. So again, we just have, after the 4th decimal point, a change in mutual information. And we can also take a look at the evolution of mutual information if we do now multiple iterations of decoding. And also in this analysis, we see that the red line here is the optimal non-uniform solution, and the restriction to uniform boundaries at the variable node or at the check node still gives very similar performance. And for example, if we do a restriction to the minimum approximation, we see more degradation here. And since the minimum approximation is used in practice often, we know that the uniform will work well too, probably.
Yeah. We recently have sort of rediscovered min star. There's a little offset that you can compute that makes min better. I'm wondering how the loss you're seeing would compare to min star as opposed to min.
Well, if you do the min star, you end up again with a high resolution number, right? Because you have this correction term, which is some real valued number.
Well, I'm going to push back and say, no, I can do min star before the quantize, you know, in the high precision realm before I quantize.
Yeah. Actually, then you end up with the same as we're using this update here. So here you don't have any loss in mutual information at the output message, but instead of using those equations, probably you can also use the min star operation. This is just a different domain.
Right. I guess something I'm trying to figure out is why do people use min at all? Because min star doesn't add a lot of complexity and performs so close to the original equations. I mean, we do it ourselves. We've written a lot of papers where we use min sum, but we just recently were working with a company that wanted our FPGA code, and they said, well, we want it to be much closer. And we thought, oh, min star. And then once we implement, it's like, wait, why weren't we always doing this? Anyway, just a comment. Keep going.
Yeah, thank you for the comment. Okay, so now we saw that it works well with the mutual information, but how about actual Monte Carlo simulations? And this is what we did on this slide here. And here the mutual information results are confirmed also in terms of frame error rates for a high rate code. And we see that the performance is very close, independent of what configuration we have. And for comparisons, I've shown here also offset min sum decoder, which can be seen as a conventional benchmark. And we gain roughly 0.1 dB in performance compared to the conventional approach here. If we switch to 3-bit resolution, we can see that we can achieve similar performance as a 4-bit conventional decoder. And the results
Wait, I'm sorry,
confirmed.
I missed something. Can you go back 2 slides?
Yeah,
This one.
of course.
Okay, so it looks to me like you're doing better than the 4. Oh, I see. With 4-bit, you're beating offset min sum, and you go down to 3 bits. Now you're about the same as offset min sum, but you're only
Yes.
3 bits. I see. Got it.
Yeah, right. And we can also look at a medium rate. So we have a rate 1/2 code here. And again, we see that the performance of the uniformly restricted decoder is very close to the optimal, the red one here. And here we use 4-bit for all the messages. And we again see a gain of roughly 0.13 dB compared to the offset min-sum decoder. And going to 3 bits again shows that we can approach the 4-bit conventional decoder performance.
Great.
And yeah, here's one last slide concerning the complexity of the node operations. So for the check node, we have several options. We can do it the non-uniform way. We can then have the computational domain and non-uniform boundaries. We can make the restriction to uniform boundaries. Then we lose the complexity dependence on the resolution of exchange messages, because we don't need those comparisons. So compared to non-uniform, the uniform seems to give a lower complexity, but still the minimum approximation seems to have lowest complexity, because we can just implement it using low bit with comparisons. And therefore I marked this here as green, because it seems to be the most practical way for the check node. And yeah, the variable node, we don't have a minimum approximation. So the lowest complexity seems to be here using the uniform quantization approach.
Are you saying that it doesn't matter that whether you use uniform or non-uniform quantization if you're just going to take the min anyway?
No. Yeah, so what do you mean by it matter?
Well, I guess, you know, you talked about, well, I guess there are 4 different ways to handle the check node: non-uniform, uniform, min. So basically what a lot of people would call min-sum, and offset min-sum. And if I do min, you know, you don't divide min-sum into uniform versus non-uniform. So when you say min-sum, are you using min-sum with a non-uniform quantizer? Is that the assumption?
Well, the minimum approximation is independent if we do uniform or non-uniform at the variable node. So it works with both configuration. It's at the variable node. And yeah, we saw that the performance is very similar, whether we use non-uniform or uniform at the variable node.
So you're saying, as far as you're concerned, it doesn't matter, right?
Yeah.
If I wanted to use non-uniform, I'd basically be quantizing the messages that come out of the variable nodes non-uniformly and doing min-sum at the check nodes, but then have the check nodes quantize uniformly so that we get the lower complexity when I do the computations at the variable node.
Yeah, but you still have an improvement a little bit if you do non-uniform with a min approximation compared to uniform with a min approximation, but it's very small. Yeah,
it may not matter, but I could if I wanted. All right.
Yeah, you could combine any combination here of check and variable node mentioned on the slide.
Yeah. All right. Thanks.
So yes, an interim summary. We saw that uniform quantization causes only minor loss compared to the non-uniform way. And at the same time, we reduce the node complexity and decoding delay a lot with the uniform approach. And yeah, the 3-bit decoder showed up similar performance as conventional 4-bit decoding. Yeah, so this was the first part. And if there are any questions left, I'm happy to take those. Okay.
Actually, sorry,
Yeah.
okay, I'll go first. So it seems like you are individually, running the belief propagation, collecting the LLRs, getting the graphs, and then learning the mutual information and then how to bound them from the statistical data. Is that correct?
Yes, yes.
But doesn't quantizing change the distribution? So like if you quantize the variable nodes, shouldn't you be using the quantized values to do the mutual information for the check nodes? It seems like you're doing them independently instead of what seems like they could be done together. Could they not be?
Yeah, so what we do can be maybe described here by that picture. So we first generate or compute the mutual the joint distribution between X and the message from the channel. So this is the starting point. And from that, we can generate the input distributions for the check node and perform the update according to the check node behavior. And then we have the output distribution. And this output distribution from the check node is then used in the iteration here to compute the variable node update, where we have the summation and we can keep track of the probabilities throughout the operations here. And in this way, we can track the distributions for every iteration. And this model we use here does neglect the cycle effects. So this is the approximation here.
So just to rephrase again, you are having different quantization at every iteration as well? Is that what you're saying?
Yes, the quantization levels change in every iteration. So in every iteration, we compute an optimal quantization, which maximizes the mutual information within the exchanged messages.
Okay. And the data necessary to store these is fairly small in comparison to, because adding the non-uniform ones, now you have to store this lookup table for every single iteration. And I'm assuming that this is a high rate code. I guess you don't need to iterate that long. Oh, okay. All right, I was just wondering. Thank you.
Yeah, thanks for your question.
Yeah. Hi, Philip. My question is, so is your decoding structure? I mean, does your decoding structure only use non-uniform quantization for the channel LLRs, the channel observations? And for all the other check node and variable node operations, what you observe is it actually doesn't matter whether or not you use uniform or non-uniform quantization. Is that true?
Yes, so for the channel quantization, you could also use the uniform quantization, and it will show very, very similar performance to the non-uniform quantization. Okay. And also the variable and check nodes can be used with uniform restriction, and the performance will be very similar compared to using non-uniform boundaries here.
Okay, so I think I might be lost somewhere, because for me it looks like what you're trying to show is that the uniform quantization actually performs as well as the non-uniform quantization, right?
Yeah,
I mean,
it's a little bit degraded, but the performance loss seems not to matter that much.
I think the key thing, Lin Fong, a way to find the intuition behind what is surprising at first is that when we went to non-uniform quantization, we did two things. We made it non-uniform, and we made the quantization depend on the distribution at every iteration. And I think the insight here is that Philip is saying, actually, you don't need to be non-uniform necessarily if you make your uniform quantizer depend on every iteration. So as the distribution is changing, you're constraining it to be uniform, but it's not the same for every iteration, so that it's as you are getting closer and closer to a decision, that the delta of the uniform quantization is spreading out.
Oh, I see. So the trick is how to design the delta. You use
Yes.
the okay.
Yes, yes.
Okay.
And I think that's a fun way to think about it. And that also means that the quantization tables per iteration now can be represented by a single number. And it's not just, it's confusing to me, that delta. Oh, I see.
Yeah, so so like Phillip still uses the density evolution to do some optimizations for the mutual information, but he restrict
Yes, yes.
on the
So that,
uniform
yeah.
quantization. So yeah, I'm interested with the what about the higher resolution? Like if you do the like 4 bits, I don't know, maybe currently you're doing 4 bits, but what if you're doing 5 bits? Maybe that, yeah, okay. But what if 3 bits? If you like reduce your bit width, will the non-uniform quantizations, will the uniform quantization still performs as well as the non-uniform quantization?
Yes, I have included results on this slide here, for example, where we have the three bits, and you can see that the red line is below the lines with the uniform restrictions. So again, we see that uniform quantization also works well if we go down to 3 bits, for example.
Okay. Yeah, thanks, Phillip. That answers my question.
Thank you for your question. Yeah.
Phillip, I have a question regarding you plotted here bit error rate. Do you have plots for the word error rates?
Oh, right, yeah.
See,
Yeah,
okay, what's
for the high rate code, I only have those plots.
I see. Okay. Have you observed anything unusual at the low frame error rates when you quantize a lot?
Yeah, if you go to very low resolutions, it can impact the error flow, of course. So
Okay.
if you, yeah.
Oh, that's interesting. That would be very interesting for us to know. Did you see any flooring yourself? And if so, could you show us that? Like non-uniform versus uniform, did you notice some flooring at like 10 to the minus 10 or something?
Yeah, in this work, I have not simulated down to those levels, but from previous work, we saw that at least for non-uniform quantization, there seems to be a little bit lower error flow if we use 4-bit instead of 3-bit, for example. And those error flows were around 10 to the minus 12.
Also, Phillip, you have shown here block size of 8,000 and 2,048 here. Do you have a shorter block sizes to see what's the effect of quantization on that?
I have it not available yet, but this could be something we should take an eye on in the future.
And mostly you use regular type LDPC code rather than irregular type, right?
Yeah, we have not tweaked the design yet for irregular codes because this involves some more challenges in the design procedure. So this is something we will do in the future work.
Okay, thanks.
Great. Thank you. You can see that you're getting a lot of questions. Might be, yeah. So that's the good thing about talking to people who are interested in exactly what you're doing. So
yeah.
But I think this this greatly reduces the complexity. And by the way, for this regular case, I think the people, I mean, the people who are working on the memory system, the storage system, We'll be very interesting. We'll be very interested in your work. Yeah. Because they use the very high rate and long block length, regular or semi-regular LDPC codes
Yeah,
in
in
their
fact,
system.
Philip, if you want to present your work to that community, they just extended the deadline. Samira and I were up until midnight getting our paper ready so that we would meet the original deadline, which was 3 o'clock or 4 o'clock this morning. But they extended the deadline for another 2 days. And this is an unusual workshop where it doesn't have to be original work. They would love for you to submit your, it's a San Diego workshop, the non-volatile memory workshop. Samira, can you drop the link in for Philip? In case you want to go to San Diego in March, I think this would be a very good, the community would be very interested in your work. And all you have to do is prepare a 2-page extended abstract where somewhere in the first paragraph you say, really, this is my paper that I already presented at ICC. You can go there for the details, but let me give you a brief summary of what's important. And then there's a very high acceptance rate for good work. I don't know if that's interesting to you, but I'll just mention it. Because Lin Fong is right. You may not have realized it, but one of the biggest users of very efficient LDPC decoders is the flash memory community.
Yeah, thank you for the proposal. And indeed, I'm not very aware how much LDPC codes are used in those specific areas. So it's very good to get some inside knowledge there.
Yeah, it might be fun. Actually, Lin Fong, before he went to MediaTek, he interned at the 2 major competitors with each other in the flash memory space. So he knows what he's talking about, has seen the actual, well, I'll shut up. Okay, so good.
Yeah, thank you for the proposal. So I think I can continue with the second part.
Go ahead, yes.
Agree. Okay, so this is about the work we presented also at the GlobeCom conference, and title is called A Variable Node Design with Check Node Aware Quantization, Leveraging 2-bit LDPC Decoding. And you can access this work also on arXiv. And again, we start with the picture I presented to you. And now the question is, can we improve performance further for those low bit with message exchange? And this paper aims to do that. So first, we will look at what has been currently done to optimize the performance. And here we can see a variable node update where we have a channel message and a check node message. And then we optimize the operations here to maximize the mutual information within the output message here. So as you saw, we can do it in a computational domain way where we have a translation to log likelihood ratios, the addition, and then in this case, the uniform quantization, because it gives us low complexity. And the implementation for the uniform quantization is very low, and this is why we use it here. And then we just need to tweak the delta here and the right shift value, which is an integer, to optimize the mutual information. At the check node, we assume here the minimum approximation because we saw that it gives very low complexity, and the minimum approximation is very simple to compute. Just take the product of signs and the minimum of the 2 input magnitudes in this case here. And we also came up with hardware implementations using logic gates. So you can see that if we use 3 bits, the minimum approximation updates can be realized by using 9 logic gates. And now we also have implemented it for, or we designed it for the 2-bit case, and we see that we just need 2 logic gates here. And so there's a high motivation also in terms of lowering the check node complexity when we move from 3 bits to 2 bits. So we can save some complexity if we go to 2 bits for the check node update as well. And most importantly, we would save complexity on the number of exchange message bits. And now, what is the contribution of this work? We extend basically the optimization at the variable node to consider the subsequent check node behavior. So instead of maximizing the mutual information at the output of the quantization here, we tweak the quantization here to have maximum mutual information after the check node update. So this is what the check node aware design is referring at. We can do that similarly by just tweaking the delta and the right shift here to maximize the mutual information between the check node message and the target node here. And here we have some first simulation results. So what you can see here on the left axis is the mutual information after the variable node. This is the red one. On the right, you can see the mutual information after the check node update. And on the horizontal axis, you can see the boundary placement. In case of 2 bits, it's just a single boundary. And when we tweak this placement, we can see how the objective function changes. And we notice that if we optimize for highest mutual information here at the variable node output, the optimal boundary would be placed close to 3. And if we use now the new objective, the boundary would be placed completely differently. And it will give us much higher mutual information at the check node output than the result with the red boundary here. So we gain higher mutual information at the check node output. And we can also track the mutual information across the iterations. And in this case, the effect will accumulate. So if we gain something in the first iteration, it will also give us benefits in the subsequent iterations. And this is what you can see here. So we track here the probabilities of the exchanged messages and can compute the mutual informations. And you can see here on the left, the dotted line is the mutual information of the variable node message, and the dashed line from the check node message. And the APP mutual information just includes the non-extrinsic message here. And we start now with the same channel conditions here. And if we look, for example, here at the check node mutual information, we see that after the first iteration, we already have some gain in case of the aware design compared to the unaware design. And if we move along the iterations, we converge much faster than if we do the unaware approach. And we also have higher variable node mutual information after a few iterations because the input to the variable node is much more reliable after a few iterations. So also in this area, the aware design can surpass the unaware design. And we just need 10 iterations to converge instead of 30 for this particular example.
Can you clarify what the dashed, dotted, and solid lines are?
Yeah, the dashed line here is the mutual information, which is computed from the messages. Yeah. Okay.
Thank you.
Good. So, and again, we can take a look at the bit error rates for high rate regular code here. And we see that in particular for 2 bits, we see significant gains of 0.18 dB. If we move to higher resolution of the exchange messages, so for example, the 3 bits, the gain reduces to 0.05, and at 4 bits, we just have 0.02 dB. So this aware design seems to be very promising for very coarse quantization of the exchange messages.
What's the 4? It says 4.2. It's
Yeah,
not,
4
it's
is
not
the
4.
channel.
Okay.
It's a channel bit width. Yeah.
Thank you. Okay.
And we can also do it for a medium rate code. And there we saw gains of up to 0.2 dB in case of 2 bits for the exchange messages. And also the gain reduces if we go to higher resolutions for the exchanged messages. Yeah, so yeah, in summary, this work presented a new class of mutual information maximizing decoders because we extended the optimization objective. And we observed gains of up to 0.2 dB, in particular for the 2-bit decoding. And 2-bit is also very interesting because it can reduce the check node complexity, as we showed, by a lot. Yeah.
Wow, what a great presentation. Very exciting result. Do we have any questions? I know we kind of slowed you down with the first presentation, but I think now we're all kind of in sync with what you're doing.
Yeah, you have shown some performance with the variable node degree 4. Have you compared that with degree 3 to see that in terms of frame error rate, especially if you go below 10 to the minus 6, which you don't have, you see the difference using degree 4?
Yeah.
I always fan of degree 4 because it essentially may eliminate many non-code word issues in the belief propagation, especially in the trapping sets and so on.
Yeah, so
it's good to compare, degree the same rate, but with 3.6 rather than 4.8.
Yeah, I also looked at 3.6 example, and interestingly, the gain was not that large for this degree.
I see.
On the degree distribution, and so it can turn out to have not that much of a benefit if you use a degree distribution which is different. And this is something we have to investigate further, in particular also for irregular LDPC codes.
Very nice. I think we're getting close to time, so I want to go ahead and let you tell us a little bit about your third topic.
My third topic would be about the horizontal and vertical layer decoding, which we presented at the Phillip conference last year. And in this work, we looked at quasi-cyclic LDPC codes, which have this nice structure where you have a base matrix, which fully defines the code together with a lifting size. And from that, you can come up with a full matrix, and then you could perform message passing to do the decoding. And one option to do the decoding is a well-known flooding schedule, where you perform all the check node updates in parallel, and followed by all the variable node updates in parallel, which completes one decoder iteration. And the advantage is that it is highly parallel, but it has slow convergence behavior compared to the layered schedules. And one option for a layered schedule is depicted here, which is known as the vertical or also a shuffled schedule, where we partition the parity check matrix into layers. So we have those vertical layers, and each layer corresponds to a group of variable nodes where we perform full updates, followed by partial updates of all the check nodes. And so, for example, we do first partial update of all the check nodes, followed by full updates of all the variable nodes of the first group. Then we have again a partial update, followed by full updates of the variable nodes here, and so on. And this completes one layered, vertical layered decoder iteration. And since we improved the reliability of the messages within one iteration, we have a faster convergence speed. And the structure of the QC code is also beneficial for implementations. And we also observed a lower error flows when doing a layered schedule instead of a flooding schedule. And another option is to organize the matrix such that we have a horizontal schedule. And now we have the roles of variable and check nodes basically exchange, and we have partial check variable node updates and full check node updates. And for example, in one iteration, we would first update the group of check nodes here corresponding to the first layer, followed by partial updates of all the variable nodes. And this can be continued, which completes one decoder iteration. And we have similar benefits as for the vertical schedule. And to make estimates about the decoder complexity in this work, we came up with a conceptual decoder implementation. So it's not a real hardware implementation, but it should model basically the hardware on a simple level. So what we did here first is that we unrolled the decoder iteration for the horizontal schedule in this case. So we first have some shifting operation which sends the messages to the check nodes where we do a full update here. And then we have a shift back to the variable node location where we do the partial updates. And the shifting is realized, can be realized by barrel shifter, for example. And the variable node, we use extrinsic messages from memory and the new message from the check node to perform an update for the message to the subsequent check node group, which is the second one here. And then we do the check node update, and this completes the unrolled decoder iteration. For the variable node in this work, we assumed the uniformly quantized update. So instead of having non-uniform quantization, we just perform the bit shift operation here to achieve the uniform quantization, which gives us improvements in terms of delay. And now one might ask, so we still have here high complexity when we look at the routing congestion here, but we can reorganize it such that only parallel wires occur, which is beneficial for hardware implementations. And we can further reorganize this if we exploit the third dimension. So all the parallel wires here become short. And in this way, we have now a model to make estimates on the complexity of the full decoder, because the routing network, the routing network's complexity lies fully within the barrel shifting unit here. And then we have also some complexity at the check nodes and the variable nodes. And Yeah, similarly, it can be done for the vertical schedule. So here we have also partial node updates at the check nodes instead of variable nodes. And we expected here the 3 minimum update as in reference 1. And we can come up with a similar model to make estimates about the complexity. And one important question we wanted to address is how important is it to optimize the node complexity versus the network complexity? Because we always work on improving both aspects, but I think it's important to get an idea how important the complexity reduction is with respect to each other. And so we can now assign resources for those simplified models. So for those check node boxes, we can assign here complexity for additions and comparisons by using, in this case, a carry ripple structure. And for the barrel shifter, we use the results obtained in the work from Boutillon. And now we are able to compare the node versus the network complexity, which we did here for the toy example of check node degree 18, variable node degree 3, and the lifting factor of 512. And in the results, you can see that the check node seems to have the lowest complexity in terms of number of gates per edge and iteration. So we normalize the complexity for each edge and iteration. So we need 11 here. And for the variable node, it's 70. So this indicates that the variable node complexity is much higher than the complexity at the check node. And for the network, we see that the complexity scales with the bit width. So if we have more bits to exchange, we need more barrel shifting operations. And if we have, for example, a bit width of 3, which is necessary to achieve good performance, we see that the network actually consumes most of the part of the resources. And you can also look at the vertical schedule numbers and see that the partial update of the check node has some higher complexity, and the full update of the variable node is a little bit more efficient than a partial update as in the horizontal schedule. And the flooding schedule has the lowest node complexities, but we need probably twice the number of iterations. So it's a little bit out of the game due to that property. And this is my final slide here. So here we compared the performance using coarse quantization from 2 to 4 bits. So we saw that the network consumes most of the complexity. So it could be interesting to go to 2 bits and to reduce that complexity. And if we look at the performance, we see that for the high rate code here, we lose some performance by going to 2 bits. But maybe it's fine for the application. So maybe the application, it's more important to have a low complexity instead of the last 0.2 dB gain in performance. If we go to 2 bits, we can reduce the barrel shifting complexity by a factor of 2 compared to 4 bits. So this is what we would gain by selecting an even smaller bit width. However, if we look at the average number of decoding iterations in an early termination decoder, we see that it increases with lower resolutions. So the gains we get here are somehow reduced by a higher amount of average number of iterations. Which was observed here to be 1.5. So overall, we will gain something by going to lower resolutions, but there's a trade-off. And this completes the talk here. So we saw that the barrel shifting requires most of the complexity, and the bit width reduces the complexity proportionally, but increases the average iteration count. And for the vertical schedule, we required slightly more average iterations. So there's a slight advantage maybe for the horizontal schedule, but the final choice depends on the target architecture. So there's a demand for hardware implementations, and yeah, we look forward to maybe have some cooperations in that area to get a better idea what's the best choice for the practice. And in future work, yeah, we plan to extend the proposed concepts to irregular codes. In particular, 5G codes are probably very interesting. Yeah, we can apply then uniform and check node aware techniques. Maybe we can also do a more advanced setup, which is called here protograph aware density evolution. Yeah, horizontal and vertical layout scheduling should be investigated too, and rate compatibility is important as well. So this is the literature which has been used in the first part, second part, and third part. And yeah, I would like to thank you for your attention and nice questions. And if you have still some left and energy left, you are free to ask.
Do we have any questions? Thank you. Oh, yes, let's go.
Yeah, I have a question on the slide 43. You have shown 32-bit horizontal vertical performance here compared to the 4 and 3-bit. At 10 to the -6, they cross each other.
Yes, this is an effect we also notice. It's probably due to cycle effects where the belief propagation decoder is more sensitive than the quantized decoders.
I see. Okay, that's interesting. Yeah, thanks.
Thank you. Well, this has really been excellent, Philip. I think we're going to have to let people go. But I wanted to say before we do that, I put a note in the chat that we have a team that does FPGA implementations of LDPC decoders. And it might be fun for our team to implement some of your ideas and see, how it plays out on the actual FPGA. So that might be really exciting for us. So something to think about. Anybody else? Okay, so people are free to go now. Thank you for everyone for coming. And let's see if there are any more questions before we stop the recording. Any more questions? Okay, so I am going to add my virtual applause there. And I'm going to go ahead and stop the recording. Thank you so much, Philip, for this excellent talk.